Hi, here we are again, lesson 2.1. Yesterday we talked about uniform and normal distributions. Today we're going to continue our discussion of distribution shapes by talking about skewed and bimodal distributions. Uniform and normal distributions are both somewhat symmetric. That is, they have reflection symmetry around some center. Today's distributions are not symmetrical. So we're going to begin by talking about a distribution that is skewed. And a good word to replace skewed with, a good synonym, is stretched. And you can see in both of my pictures that I have the majority of data at the high end here, but then it tails way off to the low end. And this one is the opposite way. Skewed distributions have the majority of data at one end or the other, one end, and stretch in the opposite direction. Now, we can have skewedness in either way. This one, where you consider that it is stretching down toward the left, this one is called skewed left. So the direction is the direction that it's stretching in. This one would be skewed right. And I can give you an example of a distribution that is skewed left. If you think about the stamp date on pennies, they produce lots of new pennies. Every year more and more new pennies come out. So you get a lot at the newer end, but old pennies are still in circulation to as great an extent. So if you were looking at the year that was stamped on a penny, that would be a distribution skewed left. Okay? In lots of cases, skewed distribution have the data clumped at one end because of some natural, this says wall, that is some value that it can't go beyond. If you look at the plot that's shown here, grade point averages of 62 statistics students. Each dot, it says, represents 2. But it has clumped down here at the high end because there aren't grade point averages higher than 4.0. That's as high as it can go. So the natural wall here is the limit. Actually, it's the upper limit of GPAs, which is 4.0. Thank goodness nobody had a GPA of 0 down there, because that would be bad. Since the mean of a distribution, folks, is really highly affected by big values, extreme values, either real big or real small, it isn't the best measure of center for a skewed distribution. In a normal distribution, the mean is good because it's right in the middle. The mean is not in the middle here. Rather, you should use the median to describe the center of a skewed distribution. And to find it, you look for the data value that will separate the distribution into two equal-sized pieces. Equal-sized pieces. So if we had 31 dots here, we'd be looking for the 16th dot, and that would be the median in this distribution. The standard deviation, again, is not the best measure of spread in a skewed distribution because standard deviation really measures how far things are from center, and at one end it's way farther from center than the other. So instead of using the standard deviation, you use what's called the interquartile range. And some of you might remember that. Interquartile range. And folks, that's the middle 50% of data. Okay? It is found by taking the third quartile minus the first quartile. And if it's been a while for you since you thought about quartiles and percentiles, let's just give you a quick refresher. To find the median, we said if we have 31 dots, we divide by 2, that gets us 15 and a half. we need to be right in the center. So on the 16th dot, that's where we would be split. That would put 15 on either side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here's the median for this data set. To find the quartiles, now you find the median of each half of the distribution. So now we've got 15 values down here. If we go for the 8th one, that'll put us right in the middle, because 15 divided by 2, 7.5. So we look for the 8th dot. 1, 2, 3, 4, 5, 6, 7, 8. Here's Q1. This was the median. And we need to have the 8th dot past our median. So 1, 2, 3, 4, 5, 6, 7, 8, right in here. That's Q3, third quartile. So if I were going to write a summary sentence to describe this distribution, specifically the one that we're looking at, I would say this distribution is skewed, and I hope we're remembering the skewedness is the direction that it's stretching. It's skewed left, centered at 3 point, let's see, that's 3.5, so 3.4, with the middle 50% of values between, and now we're going to say that would be 2.9 and 7, 2.9 and 3.7, and I hope I got those numbers right. Okay, to get these summary statistics, because it's not always easy to count dots, your calculator can do this for you. It's called one variable stat, and you find it at stat right to one variable stat, one var stat. And if your data is in the first list in the calculator, you just press enter. Let me show you what I mean. I have brought my calculator up, folks, and I've entered the data into the lists of my calculator by pressing stat and enter. And don't worry about writing this down. You'll get lots more experience using this. Into list 1, I entered the grade point averages, and really some of these are guesses on my part. However, to find those summary statistics, the mean, the median, the standard deviation, the quartiles, it's stat and then arrow over to calculate. Then the first option there, one var stats, is what you want. I'm going to go ahead and hit enter. And my calculator is a little bit newer than some, so yours might not look exactly like this, but leave frequency list alone, and we are looking in list 1, so that's okay. And then just go down and calculate. And as far as reading all these things, some of them are not necessary for us today, but X with the bar over it is the mean. That's the arithmetic mean, around 3.3. To find the median and the quartiles, you arrow down. They're farther down in the list than this. You can see that we have 1.6 is the smallest value. The median, 3.45. Again, that's more specific than we got, because we weren't using the decimals. We were just saying right in here around 3.123, we said. The quartiles are at 3.05 and 3.75. Okay, that again is a very useful tool to have in your calculator. So it was stat over to calc, then one var stat and enter. Alright, the last thing that we need to talk about today is the bimodal distribution. And a bimodal distribution really just means a distribution that has more than one peak. Some have more than 2, okay? But bimodal is what we usually call them. When a distribution looks like this, there's usually a reason why. The one that you're looking at is life expectancy of females by country on 2 different continents. Well, if you're talking two different continents, by the way, Europe and Africa, then yeah, life expectancies are very much different there. So it would make sense that you have two people groups you're talking about. In a situation like this, you should give the center of each group because the center of the distribution doesn't mean anything. It's somewhere right in there. It really doesn't pertain to either those life expectancies in Africa or in Europe. Give the center of each group and say why there's more than one group. All right. Just to finish out our discussion today, I'd like to have you be introduced to 3 other words that are used often when describing distribution. A gap in a data set is a spot, or if you think about it, a spot along the x-axis where there is no data. Now, you and I may have different definitions of what is a noticeable gap, but if you look at this distribution right in here, there's a set of, say, 3 years from maybe 68 to 71 where there is no data. That's a gap. Okay? A cluster is a group of data points, and again, this is kind of a subjective measurement. Your definition of cluster may be different than mine. A group of data points, but I think that in this distribution you can clearly see that there's a cluster right there between, say, 74 years old and 84 years old, okay? A group of data points. An outlier is exactly what you would expect, a data value that's way bigger or way smaller than others. So it's a data value far from other points. And there is no outlier that you could point to in this distribution. But if you had somebody up here at 100, that'd be different, okay? All right, that's it for today, folks. I want you to get out there and look at that U-try, and we'll see you in school.